Hello everyone, I welcome you to this webinar hosted by the European Nuclear Society on the topic of how mechanical calculations support nuclear safety. A short introduction of me. My name is Daniel Hackl. I'm the president of the Austrian Nuclear Society Young Generation, and I am a project engineer at JUNO Nuclear Engineering and Consulting, company based in Austria. Today, our presenter and guest is Olivier Vernhet. He is the manager of the Burgundy Calculation Center, part of Framatome, and he has been with Framatome for more than 20 years. And yeah, that's it from my side. I'll give a word to you, Olivier, and I'm interested in the conversation. Just a short note. So the presentation will be around 40 minutes, and questions after this we'll have time of about 20 minutes, 15 to 20 minutes. And the questions, please ask them in the chat, and I will then go through the questions and ask them to Olivier. So please write them in the chat, and we'll have time in the end to ask them. So now the word's yours, Olivier.
Thank you very much, Daniel. And thank you for letting me present the Burgundy Calculation Center. So, as you said, my name is Olivier Vernhet. I'm the manager of the Burgundy Calculation Center, and I'm going to speak a little bit about what we are doing in the Burgundy Calculation Center currently. So, first of all, a quick photo of the Burgundy Calculation Center. So, as it is already said in the name, we are most of all based in Burgundy. So we have around 100 people in Burgundy, but we are also based in Lyon. We have around 40-50 engineers that are based in Lyon. We work on new build projects like EPR, because Framatome is providing a nuclear steam supply system for EPR. But we also work for the install base for different operators in France and Europe and all over the world. And we are currently working a lot on lifetime extension, also on power uprates and all the different maintenance activities. And what are we doing on this type of different projects? We are performing mechanical and thermomechanical analysis. So I'm going to go through a lot about this in the next slides. On the different primary equipment, because this is our core jobs, but we are not working only on primary equipment. We're able to work on the different equipment, not only on primary, also on auxiliary equipment and also on tools, because we've got a section dedicated to mechanical sizing of tools, and I'll also provide a quick presentation of what we can do on the tools. So we perform mechanical and thermomechanical, but we also develop the calculation tools to perform these activities. So we develop finite element tools and all the different post-processors that go along with these tools. In France, we had in last years quite an important crisis on stress corrosion cracking on auxiliary pipes, and so we helped our colleagues that are dealing with these pipes, and we developed also competencies in piping integrity. We have also competencies in dynamic calculation, and we have some colleagues that are able to perform some welding simulations. All the more since we develop a welding code in Burgundy Calculation Center. So we are able to perform calculation according to different norms and standards in France and in Europe. Most common are RCCM or ASME. You may all be aware of RCCM and ASME, and also of different norms regarding lifting and handling equipment and nuclear pressure equipment. So first, just a simplified look at our core activities. Our core activities is performing stress report. What is a stress report? In the stress report, the input data are the CAD of the equipment. Here you've got a CAD of a steam generator. Then from this CAD, we use CATIA for the CAD. Then we mesh a part of this CAD. So here you can see a mesh of the main feed water nozzle, so that we can then perform finite element calculations. Also, we must take into account mechanical characteristics, so we take them from the codes, RCCM or ASME, or we can perform some tests, because we have some facilities to perform the tests just beside the Burgundy Calculation Center. And then we take into account the loads. Which type of loads do we take into account? Thermo-hydraulical loads. we have some colleagues that provide us with those thermohydraulical loads. This can be CFD calculation or nodal calculations. And we also take into account seismic and thermal expansion loads coming from the loop calculation. You have here a small sketch of the primary loop calculation. So we have some colleagues that provide us load sets at the boundaries of our equipment. So we take into account both those load sets and those thermohydraulic loads, and we put them in the mesh with the relevant mechanical characteristics, and we perform some finite element calculations. So the code we use is called CISUS. CISUS is a code that is developed here inside the Burgundy Calculation Center. It's a code dedicated to most of our nuclear application, but also to all different kind of applications. And with this finite element code, as with any finite element code, we get some stresses. And with those stresses, we evaluate some criteria based on admissible limits. So the admissible limits are based on some tests, resilience tests, toughness tests, and also from some criteria taken from either RCCM or ASME or other norms and standards. And then we check if the criteria of the norms, RCCM or ASME, are fulfilled or not, and we write the results of our studies in the stress report and provide this to our customer. And hopefully, all the criteria are fulfilled, and we can say that our equipment is fit for operation. So now I'm going to detail a little bit what we do in the different stress reports. First thing, as I said before, is CAD and meshing. So we're able to perform some CAD modeling with CATIA most of all. Then we use a mesher called Visual Mesh to mesh our equipment. So depending on the geometry of our equipment, we may use some beam equivalent modeling. Like here, you got some beam equivalent modeling of primary loop. We can see you have pressurizer, you have the generator here, you get the reactor pressurizer and the main coolant lines over there. We also mesh using shell equivalent modeling, for example, for tanks. Here you've got a shell mesh of a tank. It's when you have some thin structures. And most of the time, we might use volumic modeling, so we are quite of we use it a lot of modeling, volumic modeling. With full hexaedric, we avoid tetrahedric modeling for precision issues. And when we study fast fracture, we also usually model some flows when we perform elastoplastic calculations. So we can see here flow modeling at the bottom left of this slide. We see the typical flow modeling that we use when we perform explicit elastoplastic calculation, and I'm going to speak a little bit about that after. So once we have the meshing, then we have to study the different failure modes. The first mode that we study is excessive deformation and plastic instability. So this is regarding primary loads. So what do we do when we want to have a look at those failure modes? We perform at first elastic calculation. This is, of course, the most common type of calculation. If we don't manage to fulfill the criteria, then we might use some other more advanced methods like elastoplastic calculations. We use isotropic hardening. We have two types of methods that we can use called limit analysis second method. I could detail if you want this type of methodologies. Also, if we need, we have a technical center just beside the calculation center where we can perform some tensile tests. We've got at the upper right an example of tensile test that we can perform here in the technical center. So if we want to have more accurate tensile properties, we may perform some tests on the material at stake. Second failure mode that we study is progressive deformations. All these failure modes are codified in RCCM or ASME. These are common failure modes that we study. So once again, we begin with elastic calculations, and if we don't manage to fulfill criteria, then we also perform some elastoplastic calculation. This time not with isotropic hardening, because we get cyclic loadings when we have a look at progressive deformation. So we use kinematic hardening. And in CISUS, We have different models that are implemented for kinematic hardening, like Chabosh, Onowang, or Arson Frederick that are implemented. So we might use those different models to perform this type of calculation, to study progressive deformation quite accurately, and most of all to be able to discard any risk of ratcheting, which is the risk that we want to discard. So here you have the type of calculation that we have performed on the Manfield line with progressive deformation using elastoplastic calculations. Then another failure mode that we study a lot, it's fatigue, also with cyclic loading. So once again, it's codified in different codes, RCCM and ASME, elastic approaches. So we begin with these approaches. If it's not suitable, then we use elastoplastic approaches, also with kinematic hardening, same kind of model I spoke about. If to optimize the elastoplastic correction factor, if it's not enough, then we might use a full elastoplastic where we calculate total strain amplitudes. So we calculate directly the total strain amplitudes to implement them directly in the minor accumulation. We study fatigue not only for crack-free material, but also on crack-like discontinuities. So we have tools to be able to study crack-like discontinuities. Like partial penetration welds, for example. Recently, different codes, ASME and RCCM, implemented an approach to take into account environmental effects. So our Cistus and our post-processors today implement the environmental effect methodology according to RCCM and ASME. We're able to implement both methodology, both extrema methodology and rainfall approaches. Rainfall approaches is a more accurate methodology that is codified today. And as for excessive deformation in the facility close to Burgundy Calculation Center, we also are able to perform some fatigue tests to perform to get some specific fatigue curve for material. Last failure mode that I want to speak about is fast fracture. So of course, when we study fast fracture, we study both brittle fracture and ductile tearing. Once again, we begin with quite basic calculation and with flowless elastic stability and crack propagation calculations. So we don't model the flows. We use only an elastic mechanical behavior of our equipment. We use to model the flow some influence functions that are codified and implemented in our post-processor. And if it's not enough, we might develop some specific influence function specific to the geometry that we want to study. We might also develop some specific elastoplastic correction factors because, as I said, we begin with elastic calculations, so we use elastoplastic correction factors, but sometimes the ones that are codified are too pessimistic, so we want to optimize them. So we might perform some specific to the geometry we study elastoplastic correction factors. If it's not enough, then we might perform some elastoplastic stability calculations. So we mesh the flow. So I provide you just a few slides before an example of a mesh with a flow model. So this is a typical calculation we perform. We model the flow, we put some elastoplastic material properties and try to check that the defect is stable. We might also perform some elastoplastic crack propagation analysis with flow that is remeshed along the propagation. And once again, we might perform some tests, toughness and crack propagation tests, also at the technical center just beside. These are the, let's say, quite a common typical analysis because in Framatome in France, the fast fracture is a failure mode that we study a lot. So we've developed different advanced methodologies to study fast fracture. Cistus is implemented extended finite element modes calculations, XM calculations. So we are able to take into account flows without modeling them inside the meshes. Also, another recent approach that has been developed regarding fast fracture. So I spoke about global approach before, but Cistus is also implementing a local approach. So we're able to perform some local approach analysis. One application of this local approach is called the warm processing effect, or the constraint effect, meaning that we are able to say that we can discard fast fracture even if sometimes we might cross the toughness curve, but only if we cross the toughness curve through by decreasing the temperature. We can also take into account some residual stresses, for example, residual stresses coming from welding. And so I said at the beginning that we can also perform some numerical welding simulations to evaluate those stresses and then take them into account into a fast fracture study with elastoplastic properties and flow mesh, for example. So I spoke a lot about the type of studies that we do, but to perform the studies we use different codes. I said that the code, finite element code that we use is called Sistus. So Sistus is a code that is developed in Burgundy Calculation Center. Along with Sistus, we developed different scripts to help us automate the different pre and post processing. And we also develop post-processors, which are, let's say, plugins that go just after Sistus, take into account the stresses that are the output of Sistus calculations, and then provide stress intensity factor when we study fast fracture, cumulative usage factor when we study factive, for example, or membrane stresses when we study excessive deformation. So we have developed all those post-processors that are compliant with RCCM, with ASME, or with different codes and standards to get the criteria required by the different codes. In Sistus, we also have a weld module that we use to perform some numerical welding simulation. So in the numerical welding simulation, we're able to calculate residual stresses and distortions also. And more recently, we tried to check whether it was interesting or not to use some artificial intelligence meta models. So we developed some meta models that are able to model the full chain of calculations I showed you at the beginning of the presentation. So going from the loadings until the criteria for fast fracture, fatigue, and so on. And so we showed that we could develop a meta model that are able to calculate stress intensity factor without going through Sistus, without going through the post-processors, only using AI meta models. And I'm going to present you the results that we had. So here you got the study that we did. We postulated defects in the weld between steam generator upper support brackets. So you can see the flow in red that we considered. Right in the middle of the weld between the bracket and the pressure boundary of the steam generator. So we postulated defects there. We went through the whole physical chain of calculation using Sistus and the fast fracture post-processor. So this helped us evaluate stress intensity factors. We ran this calculation for around 3,000 samples. So we got a training data for 3,000 samples, and then we trained a convolutional and recurrent neural network with this data, and we tested our meta model on the test data, and we get quite a good results on the test data because we get mean error of 0.86 megapascal per square root meters. And you have here an example of curves that we got. You get in orange the curve we got from the chain of calculation, and in blue the curve that we had from the meta model. So you can almost not see the difference between the curves, meaning that the AI model is able to model quite accurately the physical chain of calculation. So instead of, say, several weeks or months of calculations, it only takes a few seconds to get the prediction through the meta model. Now, just a few examples of achievements, stress reports that we performed recently. So we are in Framatome. So of course, we performed the stress report of the components provided by Framatome, most of all EPR components, like for Flamanville 3, for Hinkley Point, EPR in the UK. We also perform stress report for the components of replacement. So in France, we are currently replacing steam generators for the 1300 megawatt power plants. So we perform the stress report for these steam generators of replacement. We also provided steam generators replacement for South Africa, for Cuberg, for ESCOM. So we perform the stress report for these components too. And now we're beginning to perform stress report for EPR2. So the new EPRs that are beginning to be built in France. So six EPR and maybe 8 more. So we're beginning the stress report for this big program. Also, we're performing a stress report for submarines. Because we have a defense section, so we're also able to perform some defense justifications with the same kind of tools, same kind of approaches. Let's go a little bit more in detail in another project called in French VD400, VD4 1300. So 1300 is the power of the power plant. VD4, VD stands for decennial visit. 4 stands for the fourth decennial visit. What is a decennial visit? It's specific to France. It's a key inspection that is performed every 10 years, in which the operator go and inspect the whole power plant, and during which we also have to take into account the operational experience of the 10 last years and update our different justifications. Since, as I said before, we perform justification when we provide a new equipment, we are also involved in the update of the justification every 10 years in the frame of the decennial visits. So, for example, in VD4 1300, we also updated our justification for the 1300 megawatt power plants. This was a big project last year because we had the safety authority milestone for the end of 2025. So we had to end all the justification for all different equipment for end of 2025 for EDF, so that EDF could provide the file to safety authority, and of course with all the different criteria I just spoke about fulfilled. So this was quite a huge work for us. And so we managed to to finish all the different calculations by the end of last year and to fulfill all different criteria. But of course, this required a lot of efforts. There were around 40 people working on this kind of project. We used a different methodology I spoke about, basic linear elastic calculations, but also isotropic and kinematic hardening elastoplastic calculations sometimes, flow modeling, full 3D explicit modeling, and so on. And we also had to upgrade some bus processors to be fully compliant with the requirements of the safety authority in France. This was also quite a huge work in terms of planning, because since we had to comply with the different criteria, sometimes we had to implement more complicated criteria which were not supposed to be performed at the beginning. So we have the planificator that is dedicated to the planification of all the Burgundy Calculation Center. And of course, we had a lot of interfaces with the project, with the customer, with the safety authority, and also with our colleagues providing us input data. Another example, for example, on main coolant lines, we had to, in 6 months, to perform more than 60 elastoplastic calculations. So you can see the typical elastoplastic calculations we perform with the flow mesh here. So to study, to provide justification of main coolant lines, we had to, in 6 months, perform 60 elastoplastic calculations. So these were not foreseen at the beginning, but we had to, and so we had to change our organization to meet the expectations of the customer on this topic. I'm done with detailing the typical calculation we performed recently. I'm going to speak a little bit more about the factory because, as I said, Burgundy Calculation Center is located in Burgundy. It's located in Saint-Marcel, close to Chalon-sur-Saône, and we are located inside the factory. So here you get some photos of the factory. So you get some photos dating from 1974, when the factory was built for the first time, providing equipment for the first French power plants, 900 megawatt power plants. Then we had an extension of this workshop, which occurred in 2005, to be able to deliver equipment for the EPR program for Olkiluoto in Finland, for Chinese, and for France. This facility delivered recently some equipment for Hinkley Point C for the UK. And in 2024, say a little bit more than 1 year ago, we started the manufacturing for reactor pressure vessel and steam generator for Sizewell C, other power plant in UK, and EPR2, so the 6 next power plants to be built in France. And now the facility in Saint-Marcel is beginning to evolve a lot for the EPR2 and also for maybe some other coming projects abroad. So you can see here the big extension that is currently being built in Saint-Marcel. These other extensions that you don't see in the photograph from 2025 have already been built. So this is only the last one that is still to be built. And the objective of this extension is to manufacture 1.5 EPR per year by 2028. Today it's more 0.7, 0.8, and the objective is to double our capacity to manufacture an EPR every year. And so with this extension, of course, we will have new tools, new handling tools, new welding tools. And as I said at the beginning, inside Burgundy Calculation Center, we also have the capacity to perform some sizing of tools. And so we are also involved in this big project of extension of a Saint-Marcel facility. And we perform some tool sizing for this facility. So we perform for handling and manufacturing, but also for transport. Here you can see some cradles and storage for some components. Here I think it's a pressurizer. So we perform also the calculation of the behavior of the cradles of the pressurizer. Here you can see the finite element calculation of the cradles. And of course, for the handling here, so perform a justification of handling tools, for example, here for stimulator channel head. And also for hydraulic testing, of course, when we deliver an equipment at the end of the manufacturing, we weld some caps to be able to close the equipment before increasing the pressure above the operating pressure to check whether or not the equipment can withstand the operating pressure, and check if we don't have any leaks or any flows that are being detected. And so we have to justify those hydraulic caps, and this is also performed in the Burgundy Calculation Center. This is my last slide. Just a quick sum up of our different activities. In Burgundy Calculation Center, we perform a lot of different calculations. Basing to advanced simulations, I spoke about elastic and elastoplastic calculation, isotopic, kinematic hardening, and so on. These are ISO certified and compliant with the different codes, RCCM, ISME, European norms, and so on. We're able to develop all the different softwares coming along with those different calculations. So finite element tools, plugins, post-processors that go after finite element tools that post-process the stresses to get some fast fracture, fatigue, primary stresses criterion. We recently developed some artificial intelligence models, and also we developed automation scripts to be able to automate the interfaces between the different tools, finite element tools and post-processors, for example. We have some colleagues that are able to perform some numerical welding simulations. Also other colleagues that are able to perform some CFD calculations and manufacturing simulations, also to help Saint-Marcel factory to develop tools for manufacturing and to adapt tools to improve the tools regarding manufacturing issues. Regarding testing, I spoke a lot about it in our colleagues from the technical center are able to perform mechanical tests, but also some hydraulic tests. I said at the beginning that we had around 150 engineers that are in the Burgundy Calculation Center and in Lyon. But we are also able to involve all the mechanical capabilities inside Framatome, because we are not the only one in Framatome to be able to perform mechanical calculation. We have a huge network of mechanical calculators in Framatome. We are more than 550 people in Framatome. And it can happen, and it happens during the project VD4 1300. It can happen that 150 engineers are not enough to perform all different calculations. So we also rely on our colleagues in the mechanical network. And so we might use not only 150, but the 550 people to perform the different calculations. I spoke about codes and standards. Software tools, so I spoke a lot about sisters, but we're also able to perform some calculation according to ANSYS, Custom, and Quadester, which is a code developed in EDF. And one last thing that I wanted to say is that we perform a lot of calculation, and we have hired a lot of people, because what I didn't say is that in 2021, we were only 36 people in the Burgundy Calculation Center. Today, we're 150. And so to welcome all those different people, all the different students, we had to train them. So we built a training school. It's been going on since something like 3 years, and we provide some courses for mechanical engineers. So of course, some courses in mechanics to explain how to use sisters, for example, or fatigue or fast fracture courses. Also some courses on metallurgy, because I think it's important that mechanical engineers have some notions of metallurgy, Python programming for automation script, and also, as I said, we are developing more and more using artificial intelligence meta models. So we're also providing some courses in artificial intelligence. And I think that's all for me.
So thank you, Olivier, for the presentation. I would like to move on to the questions. So please write questions in the chat, and I'll start with the questions we got before the presentation and with my presentations. But please write them in the chat, and I'll go through them then. So maybe first questions. You mentioned several types of damage. Which would you say is the most complex to predict, and why?
I would say that the most complex to predict is fast fracture, because you have two different types of fast fracture. You have brittle fracture, you have ductile tearing. It depends on the type of material, and you may have different behavior of the material. It depends also on the type of flow. It depends on the loading. We have some methodologies that are implemented in the code that are good methodologies, but that are sometimes too onerous, too penalizing. And so there have been a lot of research and development in Framatome to develop more accurate methodologies. So I spoke about some advanced methods a few slides before, like there. So it's been quite a lot of activities for us to develop those approaches, because we needed them to be able to be more accurate, because this is, let's say, a failure mode that is the most difficult to assess very accurately.
Thank you. I'll move on to a question from the chat. So for software you developed yourself, do you certify them for nuclear safety? If yes, how?
Yes, we develop Sistus. So Sistus is a code for which we perform verification and validation tests. When I say verification, we check whether our code perform the right equations that we want it to perform. So we compare with the result of equation when you perform them, let's say manually and or with other softwares, with finite element software, and the result coming out of the softwares. And we also perform validation qualification tests where we compare the results of systems with the result of some real mechanical tests. What we get from the test and what we get from systems. So we perform all those different batteries of tests. And we've got quite a thorough certification in France required by safety authority, and we are fully compliant with these requirements, and also with ASME requirements.
Thank you. Moving on to the next questions from the chat. You spoke about training for mechanical engineers. Are these courses available for people outside of Framatome?
Yeah, so we have a training school here in the Burgundy Calculation Center, close to Chalon. So people are welcome to come to Chalon to attend some courses, but we can also provide some courses at customers' premises. We just have customers to ask us the type of training that they want. We have a catalog of trainings. So if you want, you can just ask me. We will provide you with a catalog. If you have a training that you would like, we can provide you with an offer for providing the training in your premises.
Perfect, thank you. Next question from chat. So are you only using AI to perform simulation for tests, or do you also use it for simulations on the manufacturing side? As an example, tool sizing, types of material, types of welds.
For AI?
Yes, exactly. So do you...
So for the moment, we have built some meta models to perform fast fracture and fatigue calculations. We have also developed meta models for CFD calculations, and we are beginning to develop meta models for numerical welding simulation also, because numerical welding simulation are complex simulation that take a lot of time, because it's the same kind of physics as for finite element calculations, but you also add some phase changes. You add other physics inside, so of course it takes a little bit longer, and you must have also very fine meshes, so they are quite long calculations. So using meta modeling could help accelerate a lot the calculations. So we are beginning to develop AI meta models also for numerical welding simulations. But for the moment, these are only the type of simulations for which we have developed meta models, and so far we have some very good results as I exposed before with our meta models.
Thank you. Next question would be, do you have a dedicated capability to simulate additive manufacturing parts?
Yes, with our numerical welding simulation code, we are able to simulate additive manufacturing.
Thank you. Do you also do water flow calculations, for example, the water vortex and effect on vibrations in the steam generator?
So regarding this, for water flow, we are able to perform CAD calculation. It's not performed in the Burgundy Calculation Center. It's performed very close to Chalon-sur-Saône. It's performed in Le Creusot, in the technical center. We have a team of people that are performing CAD calculations, so they are able to perform this type of analysis. If we are speaking about instability of the U-bend in the steam generator, I have some colleagues in Paris that are performing some 3D calculation of the flow speed inside the secondary side of the steam generator, and then they have a tool dedicated to flow induced vibration that are able to check the fluid elastic instability risk of the tubes. So we have some codes for this, but not in the Burgundy Calculation Center with my colleagues in Paris, but of course we can make the people in touch with the right person for this.
Thank you. So I see a hand there. I'm not sure if we is the hand because of you want to ask a question or something else. I'll move on to the next questions. So can you present us some examples, types of dynamic mechanical calculations your calculation center can do? As an example, aircraft impacts.
So the typical dynamic calculation that we're able to perform in Framatome are loop calculations. So we take into account earthquake, loss of coolant accident, or airplane crash calculation. Usually we more perform implicit calculation, but my colleagues in Lyon are also able to perform some explicit calculation for like impact calculations. This is impact calculation are not performed in the Burgundy calculation center, more in Lyon, and not in my team, but we are also able to perform this. In terms of dynamic, we can also study buckling. I didn't speak about it, but we study also buckling. For the tank, we also study the tank regarding earthquake, behavior of the tank for earthquake. We study supports also regarding earthquake. This is typical dynamic calculation that we can do.
Thank you. So Lionel, sorry, I oversaw your question. So Lionel asks, what is the equivalent word in French for flow?
For flow, écoulement?
Like flow as an error. It's
flow. Sorry. FLAW.
Yes.
Defect. Let's say defect or défaut.
Okay. Thank you. Okay, so I'll just stop. Yeah. Could you present the application on which you are performing CFD simulation? Present the application. Okay.
So we perform CFD calculation for the flow FLOW inside the reactor pressure vessel, for example, going from the cold leg, going down to the downcomer of the reactor pressure vessel and going through the fuel and going out through the hot leg, for example. Perform also CFD calculation inside the steam generator. CFD calculation also in the main column lines for the whole primary loop. So we perform in the steam generator at the primary and the secondary side. It's not in my team, so I'm not fully aware of what we're able to do, but this is a typical calculation I have in my head.
Sorry, this is for CAD or CFD?
This is for CFD. We are speaking about CAD?
No, thank you. This is correct. Yeah, CFD. Thank you.
CFD, okay. Computational Fluid Dynamics, yeah.
Exactly.
Yeah, this is for CFD. It's my colleagues from Technical Center, so they're able to perform. Most of the time, they perform it for reactor pressure vessel and steam generator, which is most of the time the typical CFD calculation that they are performing. Yeah.
Okay, perfect. So next question would be, do you do any nonlinear analysis associated with composite materials and polymers? Any examples of work on concrete structures?
In Burgundy Calculation Center, we are basically specialized in metallic structures, so ferritic, austenitic, stainless steel. So we usually perform it on metallic structures, but on composite structures, it is also possible. On concrete, we are not used to perform calculation on concrete. No.
Perfect. Are your mechanical engineers of the Framatome Calculation Center participating at technical conferences for numerical simulations like LS Dyna conferences?
LS Dyna, I don't have it in mind. A lot of mechanical engineers from Framatome participate to PVP, ICON, SMIRT conferences. But LS Dyna, no. I know that my colleagues in Lyon use LS Dyna to perform the explicit calculation I was speaking about a few minutes before. But I'm not aware that they are attending any conference on LS Dyna.
Thank you. Do you also, sorry.
We also participate to NAFEMS. Yeah.
So do you also do thermohydraulic simulations?
Yes, in terms of thermohydraulic simulation, so not also in Burgundy Calculation Center because we are specialized in mechanical calculations, but my colleagues in Lyon and in Paris perform either CFD calculations, we spoke about it before, or also nodal calculations. So we provide a nodal equivalent mesh of the primary circuit or of the steam generator, for example, and we can perform monophasic and diphasic thermohydraulic calculation at the different nodes of our model to be able to compute speed, pressure, temperature at the different nodes, and these are typically the input data that we get there. When I spoke about thermohydraulic loads here, this is typical CFD calculation results, but we also most of the time we get results from nodal calculations.
Perfect. So another question is, what would you say are the benefits of using sisters over ENSYS?
Let's say ENSYS is a good software when you are using Workbench, for example. Let's say it's quite easy to use with a graphical interface. Sisters interface is maybe less user-friendly than ENSYS, but the advantage of Sisters is it's a code oriented for nuclear applications, and it has a whole ecosystem with all the different post-processors to be able to compute fatigue, to be able to compute fast fracture, and also we have implemented all the different operational experience that we've had along the, let's say, 60 years of calculations that we have in Framatome with the different laws. I spoke about Chabosh, Ono-Wang, Armstrong-Fielding, that are laws with kinematic hardening that we use to perform progressive deformation of fatigue calculations. And those laws are implemented in Sisters so that we can perform those calculations. We also have implemented X finite element mesh so that we can perform XFEM studies to perform fast fracture calculation without having to model the defects. So all the Sisters is really oriented to be able to perform calculations for the stress reports required in the nuclear engineering. One last thing is that Sisters is a code that is developed in Framatome in the Burgundy Calculation Center. It's a European code, French code, and so we don't have any problem of sovereignty regarding US or China, for example.
Thank you. So a question from Francesco, which is quite specific. Is there any prominent fluid structure interaction effect that you have to consider in your calculation activities?
It depends on the structure you study. For example, if you're studying reactor pressure vessel, or steam generator, or main column lines, the structure are quite thick. So you don't have any mode of vibration that you fear for this kind of structure. But if you're studying, we're speaking about U-bands inside the steam generator, tubes inside the steam generator. So in this case, you may face some vibration of the tubes. You may face some fluid elastic instability of the tubes. And so we study this kind of fluid elastic fluid interaction between diphasic flow on the secondary side of the steam generator and the tubes. And we have developed specific post-processors to be able to study this kind of vibration risk for the tubes. We also have developed things like this for fuel, for example, because fuel also you may have also some vibration risks and so on. So we only study vibration when there is a risk with big thick component like RPV or simulator pressure boundary, no, but with thin structure like tubes. Fuel, yes, we take it into account.
Thank you. Someone asks for contact info, so email maybe. Olivier, could you share it if you're free?
Yeah, of course. It's not very complicated. Yes, just there.
Here it is. So you can write Olivier.
Yeah, you can write directly to me, and I will redirect to any people necessary.
Perfect. So longer question. I'll come to this later. Do you perform calculations for loss of coolant accidents, blowdown events?
Blowdown events? For loss of coolant accident, yes. We perform dynamic calculations. We also perform thermal-hydraulic calculations for the loss of coolant accident. But I'm not sure to understand what is the link with blowdown event.
Yeah, maybe you can the one who asked, person who asked, can maybe specify blowdown. I'm also not familiar with it, but yeah. So fast fracture in dynamic.
Fast fracture in dynamic. This is not something that we usually do, the interaction between dynamic and fast fracture. But I know that some of my colleagues that are experts in the domain are some subjects that are studying. So we don't perform this type of calculation for first report, for example. But this is something that we study. So I could not tell you, because I'm not expert in this domain, what a typical thing that we can do. But I know that we are doing some R&D on the subject.
Thank you. So the question from Lionel, which is longer. So Lionel says, I used to calculate damages in welding seams in FemFAD software with PSD loading. So is it possible to model the welds with a library in sisters? So you add the welds on a shell structure, for example, or are you obliged to model in 3D the welds in sisters?
Model the welds for which application? To get the residual stresses, to study the weld itself, to study the structure?
Yes, I think so. Modelization of the welds, yes.
So we were to study the fatigue.
Sorry, yes.
Okay, we do both. Either we don't model the weld and we take into account stress concentration factors, for example, or we model the weld in the mesh quite accurately, and we get directly the stresses. It can also happen that we are with a weld which is a partial penetration weld, not a full penetration weld. So we get a crack-like discontinuity at the tip of the weld. And we also study this crack-like discontinuity with our post-processor. I spoke a little bit about before, but to get some post-processor that are able to evaluate the risk of fatigue in these crack-like discontinuities, for example. So we can do everything.
Thank you. So maybe a question from me. What are your interactions with other entities within Framatome who are also involved in mechanics?
I spoke a little bit about it. We have a mechanical network inside Framatome, and I'm in charge of animating this mechanical network with more than 550 people inside Framatome. And so we exchange studies within this big network. For example, if we are in the Burgundy Calculation Center have too many calculations to perform regarding our capabilities, then I go and see my colleagues from Paris or from Lyon and ask them if they have some people that are available to perform this type of calculation. And so if yes, we transfer the calculations. And I think that last year we transferred several more than 30,000 hours of activities to other colleagues in Framatome, because there were some problems of balance of capacities in Framatome. So this helped to be able to reach our milestone through the transfer inside Framatome. So this is one thing that we do with them. We also share R&D, we also share our methodology. I spoke a lot about the methods we use in Burgundy Calculation Center, but our colleagues may have other methods, so we share our methodology and try to have the same kind of tools also. And we also share the tests that we perform. So we have different meetings where we are sharing the test results, the test we perform, and the results we perform with the test among the different people working on mechanical engineering calculations.
Thank you. So, Olivier, what would you say are the developments you see coming in calculation methods over the next 5 to 10 years?
I think that we will try to have more and more accurate methods, try to interface CFD with our mechanical tools. So this is what we can also do with the CISUS, because we can take a mapping of some hydraulic loads and impose this mapping on our finite element calculation to get the traces of this mapping of loads. So I think we have to get more and more application like this, because CFD is the most accurate today methodology to evaluate some hydraulic stresses. I think also we go through development of AI metamodels, because I said before, these metamodels are of course less accurate than physical models. And of course, today I'm not going to put in my stress report results coming from a metamodel, but we know that this is quite powerful to get instant results and quite accurate results. And so this could be very useful to check some calculations or to perform some sensitivity analysis by developing AI metamodels. So I think this will be what's going in the next 5 years. More accurate model, more complex model, and also trying to check what is possible with AI metamodels for them.
Thank you. So Irish asks, so for the case that the reactor meltdown happens due to a loss of coolant accident, could we perform these calculations in sisters?
Yes, of course.
So maybe a question for me, have you, for the EPR reactor, have you modeled the part also with the core catcher? So, essentially this meltdown, and then also core catcher. Have you modeled these structures, also interaction with corium? Also, I mean, you said you're modeling more steel, not concrete, but has this been done?
So this is not done in France. Maybe it's done by my German colleagues, not with Sistus, because as I said, it's more for metallic structures. But I know the core meltdown structure is studied in Germany, but I wouldn't know what to say about this. I know that there are some simulations, but I don't know anything about this.
Thank you. So Hugo asked, do you use discrete element modeling at all?
What do you mean by discrete element modeling?
Hugo, can you maybe describe it in more detail? I'm also not
BIM
familiar with
modeling.
And we can maybe, I can ask for one last question.
Yeah, we perform BIM calculation or shell calculation, as I said at the beginning. Yeah.
Okay, thank you. Yeah, I mean, thank you all for the questions. Maybe if someone has one more question, we can ask that. But thank you all for contributing to the lively discussion then also. I see a lot of experts in this field are attending today's meeting. So Lionel asks if it is possible to get the slides.
You may send me an email and I check.
So yes, so you can ask Olivier. I'm not sure if we will publish them, but write down the email of Olivier and you can reach out if it's not published. So thank you all for attending our webinar. I think it was a success because more than 100 people attended it. I think 126 people. So have a nice day to everyone and hope to see you at the next webinar. Thank you.
Thank you very much, everybody.